Hello everyone, and welcome to our final module in our Introduction to Doka for DPU's DLI course, Applying Doka Acceleration. In this module, we'll spend some time revisiting a few of the Doka and DPU acceleration features with use cases. The goal of this module is to help shift perspective and provide inspiration for developers and systems architects to see opportunities for Doka acceleration and offloads in their own environments. In the last part of this module, we'll look at a few case studies to explain how other popular applications have succeeded in their own journeys to offload, accelerate, and isolate. Let's get started.
In this module, we'll first go through some examples of offload and acceleration features that Doka and DPU brings to developers and systems architects while exploring their potential use cases. It is important to remember that from our first module, that to use Doka, that includes not only programming APIs and frameworks and writing code, but also when leveraging runtime libraries and drivers and moving portions of the infrastructure and the services they provide either into the server at the DPU or pull those functions down to the DPU and offload them from the host. Then, we'll explore some real-world examples of existing software to show how others have succeeded in using Doka and DPUs to be able to improve the performance and security of their applications. In one case where Doka and DPUs were an inspiration for a brand new AI security framework. First, let's cover a few of the different architectural ways to perform offloading and acceleration. These examples arise from security use cases, but these architectural ideas can apply to any application in theory. Try to use these examples to help think more flexibly about what runs where and how offloads and accelerations can be invoked. Again, it's important to remember that Doka applications can run on either the x86 host or on the DPU ARM cores, so the most effective and efficient way to accelerate isn't always obvious. In this example, we'll call it the inline acceleration model. The Doka-enabled application is still built and runs on the x86 host. Packet delivery doesn't have to be based on DPDK, but the key here being that another helper daemon runs on the DPU. The security logic, checking, and enforcement occurs on the host in line with the application, and then passes the results, configuration, or other metadata down to the daemon on the DPU, where then subsequent packets of a flow can be steered around to the accelerations on the DPU and leverage the embedded switch caching functions to move at line rate. Look-aside acceleration is similar to the inline model in that applications still run on the x86 host, but the application itself is handling the invocation of acceleration features directly as an external device. For example, the regular expression engine can be invoked as a standard PCIe device from the x86 application. Also, the Doka DPI library can be fully leveraged by applications running on the host. Then, there is a security architecture that we call the DPU integrated model, where the application runs entirely on the DPU ARM cores. Essentially, all of the logic of the security application is running on the DPU, and this application is also orchestrating the invocation of the target acceleration engines for the network flows through the box. This model provides some of the best benefits in freeing up the workload from the host CPU entirely, while also being able to run the DPU in restricted mode to completely isolate the DPU from host management, and thus provide a more robust security posture, preventing the host from access to the security application in its own isolated execution space. An important way to think about leveraging DPU and applying Doka acceleration is through the lens of isolation. Isolating applications and parts of a software stack on the DPU not only provides the tamper and evasion resistance from the host, but at the same time, it's also pulling those functions off of the host CPU and providing an acceleration and offload function simultaneously. Looking at it graphically, without a DPU and its general purpose ARM cores, the whole security and infrastructure stack has to run in the only place it can, on the host and on the CPU there. The alternative for isolating access to those features from the host was to build and design them into the network infrastructure. This creates challenges for network architects and designers, as appliances that provide these features end up becoming bottlenecks and single points of failure. Thinking about how to isolate with Doka and DPUs can be the pathway to simultaneously offloading and accelerating. As we start to get into some examples and use cases, software encryption on the host can create several challenges for offloading, accelerating, and enforcing a robust security policy. If the traffic is encrypted when it leaves the host, it limits the ability of the NIC to perform other accelerations down on the stack and hides the real traffic from any policy enforcement measures that take place there. Plus, encryption is a complex and computationally difficult task for general-purpose CPUs, and we want more of those CPU cycles spent with the real applications and less time on infrastructure overhead. Thus, architectures that can separate out the encryption functions and pass clear text packets down through the DPU are much better postured to enforce security by being able to see transport layer headers and application payload data to be able to enforce security policy much more easily and effectively. If we look a little more closely at an encryption IPsec offload example, the combination of general-purpose ARM CPUs and an open-source IPsec control plane can create opportunities to offload and enforce security in transit completely transparently to the host. By running an IPsec control plane such as StrongSwan or OpenSwan on the DPU, and managing and orchestrating IPsec configuration there, we can enforce encryption as a bump in the wire as traffic transits the DPU on its way to or from the wire. This allows operators to use Doka runtime to build completely secure data center fabrics or secure a service mesh. Operators have very similar options to use Doka to offload and build secure data centers using TLS as they do with IPsec. Doka enables TLS offloads to be able to build faster load balancers, HTTPS servers, reverse proxies, etc. In addition to offloading the TLS function, it's possible to run Nginx on the DPU to further offload infrastructure overhead. Terminating TLS connections on a proxy on the DPU allows for the backside host-facing connection to be in clear text and allow for more intelligent and informed security policy enforcement. Let's take a look more closely at some real-world examples of how Doka and offloading has already impacted some existing software and architectures. In our first case study, let's look at the VMware use case. Today, we take for granted that the hypervisor, that we sometimes call simply ESXi, is actually performing a number of different discrete functions for the apps and VMs. All of the networking functions and storage and management of the application itself are all playing a supporting role for the actual compute hypervisor. That compute hypervisor manages the applications and VMs and provides all of the other powerful and flexible benefits of virtualization. But think about all of those other functions of the hypervisor. They're really infrastructure functions. What if we could move those functions down into the DPU and also functionally isolate those services and functions? Offloading the software-defined infrastructure functions is exactly what NVIDIA and VMware have partnered together to accomplish. The result is a new platform for AI, data analytics, and accelerated compute applications. This new architecture includes DPUs and GPUs to flexibly support next-generation applications and their compute needs. This allows for better scale, security, and responsiveness of VMware-managed environments when taking advantage of offloading the software-defined networking functions to the DPU. In addition, the isolation aligns with a highly secure zero-trust model. Another interesting case study for Doka is the GeForce Now cloud gaming service. GeForce now supports over 10 million members around the world, and it is an extremely complicated service to deliver where every detail matters. Visual quality, frame rate, response time, they all must be balanced with server costs and security. Many of these details that provide a high-quality gaming experience depend on the infrastructure services performing at their best. Classically, these infrastructure services run alongside of the running games on the CPU. But by offloading portions of that service that monitor and optimize the infrastructure performance and perform the necessary NAT and load balancing functions, the service can support more users more efficiently. The key is thinking about an application or service or an architecture as its functional pieces and noticing where software-defined infrastructure lives and where it's processed. How does data get in and out of your software? What amount of CPU cycles are spent used just to support that function? The other way to think about it is from the infrastructure in, rather than from the server pushing the software functions out and down. To say it differently, from an infrastructure perspective, where are your services or applications or appliances that could be disaggregated and software defined to run inside of every server, rather than being centralized and becoming a bottleneck and a single point of failure? The gaming service is a great example of how functions can be run on the DPU from both sides. Parts of the streaming service application on every server are candidates to be offloaded to the DPU ARM cores, and in the same way that NAT and DDoS protection is able to be moved out from being provided in the network infrastructure to being a distributed service and disaggregated on the DPU in each server. In our final case study, we'll take a look at a slightly different use case for Doka, where rather than offload and accelerate existing applications, it's an example of something completely new built with Doka and DPUs. Morpheus is an AI cybersecurity framework intended to help accelerate the cyber ecosystem. The Doka-powered software on the DPU acts as a real-time network sensor that collects network information and sends it to the Morpheus AI framework. Morpheus does analysis and makes a set of security policy recommendations and sends this back to the DPU. The DPU can then take action through the Doka Flow API-based policy engine. The Morpheus AI framework helps the cybersecurity ecosystem implement pre-processing, inference, post-processing, and form a set of recommended actions. To get started, it also includes a set of example models such as looking for personally identifiable information, phishing, anomalous behavior, etc. Or it's designed to help you bring your own model and just use the framework for sensing, data collection, and recommendations. An example of this framework would be for looking for leaked sensitive information, such as leaked passwords. The Doka telemetry agent for Morpheus collects and sends packet information to Morpheus AI. Morpheus is able to look through that data stream to see unencrypted data flows and make recommendations to the DPU to drop those unencrypted packets, which the DPU can take action on with the policy engine. It would be possible to also use a Doka runtime IPsec architecture to encrypt traffic after data collection and after policy enforcement, in tandem with first performing the analysis and detection on the clear text traffic on the way out from the host. That concludes our final module in our introductory Doka DLI course. In this module, we looked more closely at Doka and DPU accelerations and some of their real-world use cases. We also spent some time looking at a few case studies of specific applications and uses where Doka and DPU acceleration is being successfully applied and implemented to improve both performance for applications and users and improve security and security posture. Thanks again for joining us.